Let's look at the wave equation. This wave equation is true for any kind of wave, whether it's a water wave or a sound wave or an electromagnetic wave. Basically, it says that the velocity of the wave is equal to the frequency of the wave times the wavelength. Now, we call the electromagnetic wave equation the same thing. You'll notice all we've done is we've taken v, the velocity of the wave, and replaced it with c, because as we've said, all electromagnetic waves travel with a velocity of 3 times 10 to the 8th meters per second, which we represent by the letter c. One of the interesting things about that is that because c is constant, we could solve this for f. For example, the frequency would be equal to the speed of light divided by the wavelength, or we could solve it for the wavelength. The wavelength would be equal to the speed of light divided by the frequency. And what you'll notice is that the wavelength and the frequency are inversely related. Okay, so they're inversely proportional. And what that means is you'll notice that if I make lambda bigger, then the frequency gets smaller, because when you have a bigger number in the denominator of a fraction, the value of the fraction goes down. Or if I make the frequency bigger, the wavelength gets smaller. But what has to be true is no matter what the frequency is and no matter what the wavelength is, when they're multiplied together, they always equal 3 times 10 to the 8th meters per second. So you can imagine that some electromagnetic waves have a high frequency but a small wavelength, and others have a large wavelength but a very low frequency. And we'll see that that is what determines what type of electromagnetic wave we're talking about. That's what makes an X-ray different from visible light or different from a radio wave. Let's do a problem using the electromagnetic wave equation. WBZ, the oldest AM radio station in Massachusetts, broadcasts at a frequency of 1030 kilohertz. What is the wavelength of the broadcast? So we know that the electromagnetic wave equation is C is equal to lambda times the frequency, or frequency times lambda. It doesn't matter which way you write it. And I want to solve that for the wavelength. So the wavelength is equal to the speed of light divided by the frequency, or 3 times 10 to the 8th meters per second. And I want to divide that by 1030, but it's kilohertz. And if I want my answer for wavelength to be in meters, then I have to have my frequency in hertz. So remember, kilo means 10 to the third. So that would be the same as 1030 times 10 to the third hertz. And if you do the math there, you'll get 291 meters. So that would be the wavelength of that radio signal. So let's look at the electromagnetic spectrum. Again, we've said the electromagnetic spectrum consists of all the different types of electromagnetic radiation. So radio waves down here, all the way up to X-rays and gamma rays up at the top. And let's look at what they're showing us in this diagram. First of all, you'll notice that they're showing you the wavelength and the frequency, which we've been talking about. And what you'll notice is that X-rays and gamma rays have very high frequency and therefore very small wavelength, because as we've said, wavelength and frequency are inversely proportional. Way down at the other end, where the radio frequencies are, that's where we have large wavelengths but very low frequencies. So you'll notice just a few hundred hertz for radio waves, whereas X-rays and gamma rays are very high frequency. Some other things you'll notice here is that visible light makes up a very tiny portion of the electromagnetic spectrum. And the only reason that we care so much about visible light, of course, is that our eyes can see it. So our eyes, you can think about the fact you basically have these really cool electromagnetic radiation detectors built into your body. But unfortunately, they can only see a very narrow range of frequencies and wavelengths. Let's look at this column, which we haven't talked about, the energy. This is the energy of a photon, of the different types of electromagnetic radiation. And we're going to talk about this more next week, but the energy of a photon is equal to a constant, which is called Planck's constant, times the frequency of the photon. And what I want you to understand about that for now is that the energy of a photon is proportional to its frequency. So you'll notice that radio waves, because they have low frequency, the photons that make up a radio wave have very little energy. Whereas X-rays and gamma rays, because they're at high frequency, the energy of X-rays and gamma rays is very large. You'll notice also the units of energy that we use for photons are electron volts, which we've previously talked about. And by the way, this is basically the reason that an X-ray or a gamma ray has very high penetrating power, but anything lower in the electromagnetic spectrum doesn't. It's kind of the difference between me throwing, a bullet at a wall versus shooting it at the wall. If I throw the bullet, it doesn't have much energy. If I shoot the bullet, it has a lot of kinetic energy and can go through the wall. Same thing with photons. A visible light photon, it doesn't have very much energy. It will bounce off your skin. It will be reflected. A gamma ray or X-ray photon has enough energy that it will go through your skin, just like that bullet being shot from the gun. Okay, so just talking a little bit more about the electromagnetic spectrum. So radio frequencies, as I've mentioned, those are down here in the spectrum. So low frequency, and remember, when the frequency is low, the wavelength is big, or long wavelengths. Also, as we said, when the frequency is low, the energy of each photon is low. Okay, so if I want a high energy radio signal, it has to be made up of many, many, many photons. If we move up into visible light, this very narrow part of the spectrum, again, visible light has frequencies and wavelengths that are kind of in the middle part of the spectrum. It's a very narrow range of wavelengths that our eyes can see. It's only from about 400 to 700 nanometers. Remember that a nanometer is 10 to the minus 9th meters. And we see the different frequencies as different colors. So there's not really such thing as blue and red and green. That's just how our eye and our brain processes what we see. So when our eyes detect red light, what they're really detecting is light down at 400 nanometers. That's at the bottom part of the spectrum. And when we see violet light, that's simply our eye detecting that there is light with a wavelength of 700 nanometers. Okay, and obviously the other colors are somewhere in between. When we see all of those frequencies and wavelengths together, that's what we perceive as white light. So white light is just the combination of those different frequencies within the part of the spectrum that we can see. And if you think about what happens when light interacts with something, for example, in the book they talk about why a leaf looks green, and here's our leaf here. What happens is when white light hits it, that leaf actually absorbs all of the frequencies except green, and it reflects the green, and that's why we see it looking green. Okay, so when visible light interacts with things, the color the object appears is the only frequency that's being reflected, and all the other frequencies are being absorbed. Let's talk about the top part of the spectrum, which is the part that we're really interested in this course, which is X-rays and gamma rays. Remember, again, we refer to these as ionizing radiation because they can knock an electron out of an atom. And here, again, we're in the high frequency, short wavelength part of the spectrum. That means that the photons have much more energy. So a photon that's X-rays or gamma rays has much more energy than a visible light photon. And again, that's why it can penetrate things. By the way, in physics, usually we think of X-rays as being the part of the spectrum from ultraviolet up, and then gamma rays coming above that. But this book really differentiates them differently, that both X-rays and gamma rays can occur at that top part of the spectrum. And what's really important in terms of differentiating what's an X-ray versus what's a gamma ray is simply how they're created. So X-rays originate in electron shells, and I talked about that a few minutes ago, that when an electron gets knocked out from an inner shell, so an electron gets knocked out in some way, an electron from one of the outer shells can jump down to fill it, and it has to give off energy when it does that, and that's how X-rays are produced. In a previous chapter, we talked about how gamma rays are produced. Remember that gamma rays come from the nucleus of the atom, that when the nucleus has too much energy, it can release some energy by emitting a gamma ray. So both X-rays and gamma rays make up that top part of the spectrum. One of the things that's mentioned in the book is this wave-particle duality. And you'll notice really we've talked about electromagnetic energy in two ways. We've said that it travels in waves, but we've also said that it's made up of these particles, or kind of pseudo-particles. They're really just bundles of energy called photons. And depending on what part of the spectrum we're talking about, electromagnetic energy will act sometimes more like a wave and sometimes more like a particle. And it turns out that one of the things that's important for how electromagnetic energy interacts with matter is how the size of the matter compares with the wavelength. So for example, visible light, because the wavelength is somewhat similar to the spacing between atoms, visible light can often be absorbed or reflected by regular matter. So again, as I mentioned, when light hits the green leaf, some of that light is absorbed, but the green gets reflected, and that's why the leaf appears green to us. If we look at other parts of the spectrum, for example, X-rays, because each photon has so much more energy, it acts more like particles than it does like waves. If you go down to the other end of the spectrum to radio waves, each photon has so little energy they kind of don't do anything on their own. They just act like waves. So an X-ray photon acts much more like a particle. And so that's why X-rays can do things such as knock electrons out of atoms, because it's kind of like this very energetic particle coming in and colliding and knocking the electron out of the atom.